Okay, so today I'm going to be explaining this problem. It was one that Mr. Pabico handed out. I think it was number 8 on the handout due the weekend of the 9th. Anyways, so basically it's saying an Atwood machine consists of a cable attached to a 2.4 kilogram mass at the end of 8.3, or at one end and 8.3 at the other end. And there is a 1.7 kilogram solid disc pulley of a radius of 0.16 meters. And so the release from rest after 2 seconds determine the angular acceleration, the angular velocity, the angular displacement, and the distance as fallen. So, for clarification, one more thing we're going to need is the moment of inertia of a disk, which is just a value, which is 1/2 m/r squared. M is the mass of the disk, r is the radius of the disk. So, I'm going to draw a diagram. So we have a 0.16 meter disk, 0.16 meter, and it is also 1.7 kilograms. And then there's two masses on this. One is a 2.4 kilogram mass, one is 8.3. So I'm going to label this as mass 1, mass 2. So, and I'll also put this as big mass, big M, M1, M2. Okay. So now that we've had everything established, let's think about this a little bit. So because uh there's a moment of inertia for our pulley now. Basically this means that it's gonna take this dude has to pull down a little bit more to get this thing to spin. So we would expect, I guess, depending on the direction it's spinning, the tensions will be different. So we have to label them as tension 1 and tension 2. I'm also going to set up reference axes in the positive, and our rotation will be counterclockwise for the positive. So now that we've had everything established, we can start thinking about how to solve this problem. So we want the angular acceleration of the pulley, angular velocity, angular displacement. So basically, this will basically let us derive the velocity and the displacement of the pulley after 2 seconds. And it'll also tell us the distance that this mass has fallen. So let's set up some equations. So if we take our masses individually and make a free body diagram of each, we know that we have tension 1 pulling up on mass 1 and pulling down, m1g. On mass 2, tension 2 is pulling up, and m, that's supposed to be a 2, g is pulling down. So if we think about this, 8.3 kilograms is greater than 2.4, so most likely this is going to be down, and this is going to be going up. So now when we think of setting up our equations, oops, to adjust it, I don't, whatever. So when we think of setting up our equations, I'll do it on the next page. So let's start with the forces present. So we have tension 1 minus m1g, and that equals m1a. So I'm putting this in the positive direction because m1 is going to be traveling up. We're assuming that because the mass of m2 is greater. So now, for our next equation, we'll do T2 minus M2G equals negative M2A. So you might be asking, why is it negative? Well, it's traveling downwards. This states that our reference is upwards, is positive, and that means down is negative. So that's why we have a negative in front of this. So the only issue is if we notice, we have 1, 2, 3 unknowns and only 2 equations. And so this isn't really going to work out because we have 2 different tensions. So we need to find another equation that will come from the uh, moment of inertia. So if we kind of do a free body diagram of this big M of the solid disk, we'll notice that there is tension 1 pulling down here, and there is tension 2 pulling down here. So we're going to assume that tension 2 is going to be a little bit bigger, which will cause this to rotate. So our moment of inertia is actually going to be negative. So we have negative inertia, which is our force. And I believe we have to multiply that by a factor. Sorry, inertia is mass. We have to multiply that by a factor of acceleration, because like force is ma. So inertia um, is our mass, and this is our angular acceleration. It's a symbol for angular acceleration. And so the sum of that is going to be the rotational forces from each of these. So we have a radius here. So this means it's TR, T1R minus T2R. And so this should make a little bit of sense. So we're basically saying this is pulling down here and T2 is pulling down here, giving us a overall negative, um, basically force, causing this to turn the opposite way of our positive axis. So now we have another equation, but we've introduced another unknown. So this equals negative I. But we don't have any idea what this is. Well, it turns out that acceleration is equal to the radius times the angular momentum, basically. Angular acceleration, sorry. And if we think of this, it's like radians per second squared. If you multiply that, then I believe it should give us acceleration. I could be wrong about that. Hopefully not. So, anyways, now we have four equations, four unknowns, and we should start plugging stuff in. So, for simplicity, what I'm going to do is I'm going to just plug in what our I is and what this is in terms of acceleration and mass, in terms of things we already know. So, instead of this over here, we're now going to have what we determined our I was on the other page, which is 1/2 mr squared. So we have 1/2 mr squared. This is still negative. And if we solve for our angular acceleration here, we'll get a over r. So this is multiplied by a over r. We notice these cancel. So this equals mra over 2 negative. So now we have three equations. And what we're going to do now is we're going to put them so that we can use a what's it called? R ref on our calculator to solve these values. So what we're going to do is we're going to put all of our unknowns, I'll highlight them in red, all of our unknowns onto one side. This is an unknown, this is an unknown, this is an unknown, 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 and this is a unknown. So we're going to put them all on one side, and then we're going to plug in some values for them. So here's what I'll do. I'll do that on the next page. So we have T1, I believe, plus M1A equals it's minus M1A, bad, minus M1A equals M1G. M1G is just a value that we can calculate. In fact, I'll do it right now. For assuming M1 is 2.4, 2.4 times 9.8 is 23.52. So we can actually rewrite this as T1 minus mass 1 times acceleration. That is equal to 23.52. And this would be in newtons, I believe. But that isn't really necessary for what we're doing here. So next equation, I'm going to rewrite this by shoving this to that side. So we have T2 plus this time, because this is a negative value on the other side, plus believe the mass is 8.3 A, and that equals m2g. Mass 2, if we're assuming 8.3 is multiplied by 9.8, is 81.34. Okay, so now we have our unknowns here, actual values here. So for our final equation, I'm going to plug in the radius here instead of r. So we get 0.16 t1 minus 0.16 t2. And if we notice, all of our values are actually including some sort of unknown. So I'm going to put this on the other side. I'm going to multiply the mass and the radius of this wheel to get our MRA, which is 1.7 times the radius of 0.16. And then we're dividing that all by 2. So we get a positive value because it's on the other side of 0.136a. This all equals 0 because we've moved all of our terms over from here. So now what I'm going to do, now that I have all these values, is I'm going to set up my ref, ref, and I'm going to set up my matrix. So for my matrix, I'm going to have T1 as my first input, T2, then I'm going to have acceleration, then I'm going to have the actual number it means. So in the first one, what I'm going to input for T1, I have 1 T1, no T2s, 2.4 negative accelerations, and this all equals, I believe, 23.52. So for my second row, I have no T1s, 1 T2, I believe a positive 8.4 acceleration, if I'm not mistaken, and that equals 81.34. 81.34. For the final one, I know that I have 0.16 T1s, negative 0.16 T2s. Oops, I should write that in the T2 spot. Negative 0.16. This is separate. And I have 0.136 acceleration. So 0.136. And this will equal 0. So this will let me easily figure out what my tension is and my acceleration. Mostly, I just care about my acceleration because we're only looking for basically angular acceleration, which we can determine from having the linear acceleration and then angular velocity, angular displacement, blah, blah, blah. So now what I'm going to do is I'm going to plug this into my calculator by doing second matrix, edit. I'm going to do a 3 by 4 matrix. I'm going to plug in all these values. And then I'm going to do second quit, second matrix math, go down to the RREF, and then second matrix and put in my matrix of A. So I'm not sure if this will come up, but basically you can see the values that I'm getting. So I'm going to put this on the next page. So I get a value of T1 of 35.5 newtons. Oh, that looks like a 2. T2 equals 39.7. I'll just round it up to 39.8. It doesn't really matter. Newtons, right? And acceleration equals around 5 meters per second. So we look at this, tension 2 is greater than tension 1. So this should make sense because basically this is going to have to pull down with a little bit more force than this is getting pulled up with because it has to account for the turning of this wheel as well versus this guy's just going along for the ride basically. So now the only thing we really care about is this acceleration. So it's asking us, what is the angular acceleration of the pulley after 2 seconds have passed? So if we have a constant linear acceleration, linear acceleration is only off by a factor of r. So we're going to have a constant um, angular acceleration as well. So what we're going to do is we know that a equals r times angular acceleration. So angular acceleration equals a over r. So the r is the radius of our wheel, which we know is 0.16. So all we have to do to get this is divide 5 by 0.16. And we get an angular acceleration of 31.25 radians per second squared. That's supposed to be s. So we've answered the first part. What's the next part? The angular velocity of the pulley after 2 seconds have passed. So if we have an angular acceleration, we can figure out angular velocity. So if we look back at our kinematic equations, we have v equals VO plus AT. And the equivalent of this in angular terms is W equals WO, W being angular velocity plus angular acceleration times time. So we have no initial velocity basically in either of the terms. And we have our angular acceleration and we have our time, which is 2 seconds. So if we multiply those together, 31.25 times 2 is 62.5 radians, this time per 1 second. So this is the answer to the second part. So for the next one, the angular displacement of the pulley. So the angular displacement is basically the angle that it's turned. So if we go back to our kinematics knowledge, we know x equals, I'm going to remove the middle terms, assume we have no initial position, no initial velocity, or like zero, not no. But 1/2 at squared is our kinematic equation, basically. If we're starting with the object at rest with, yeah, at position 0 at our reference. So we can rewrite this as theta, which is the equivalent of position in angular terms, equals 1/2 angular acceleration t squared. So this is basically 1/2 of our angular acceleration, which we said was 31.25 times 4, or 31.25 times 2 because these cancel out. So our theta will actually be 62.5 radians, which is funny because it's the same as the other thing. So now the final question is the distance the 8.3 kilogram mass has fallen. So now we have to go back to our normal linear acceleration, which is 5 meters a second, and determine if our object is falling at 5 meters per second. How far will it fall in 2 seconds? This lets us use a simple kinematic equation. X equals, I'm going to remove, I'll short it, VOT plus 1/2 AT squared. So basically, no initial position, assuming this is H equals 0, no initial velocity, and we're falling down at 5 meters per second. So it's negative 5 meters per second, assuming this is positive. This is negative. So basically, all we have to do is say x equals 1/2, not 1/5, 1/2 times negative 5 times t squared, which is 4, which is point or 5 times 4, 20, divided by 2. X equals negative 10 meters. So basically, it has fallen 10 meters. So I'm pretty sure that that's it. So to review, all we really ended up doing is calculating the forces on the masses and the what would you call that? Rotational forces on the pulley. And then we used a little conversion here to get three equations with our three unknowns. And then with those unknowns, we solved for the one we actually wanted, which was acceleration. And with our acceleration, we converted it back into angular acceleration, which gave us our angular velocity and angular position. And then we went back to our linear acceleration, which gave us our total position fallen after 2 seconds. So, thank you for watching if you made it this far. And also, let me know if you have any problems you want me to go over or anything like that, because I'd be happy to do that. Yeah, thank you for making it this far. So I'll see you in the next one, maybe.